This video is going to follow up our lecture today on Euler's formula and discuss how we can apply this beautiful result to solve second-order equations with complex roots to their characteristic equation. Before we do so and look at a couple examples, I wanted to review first three facts. First, if lambda is a root of the characteristic equation m lambda squared plus gamma lambda plus k equals 0, then e to the lambda t is a solution to the second order equation my double prime plus gamma y prime plus ky equals 0. This was the first result we had when we started dealing with second order equations. Second, by Euler's formula, which we saw in today's class, we have this beautiful result that e to the it is equal to cosine t plus I sine t. And as a consequence of Euler's formula, we can combine complex conjugates to get the two trig identities that e to the it plus e to the negative it over 2 is cosine t, and e to the it minus e to the negative it over 2i is sine t. We'll be using both of these results in the examples that follow. First, we're going to look at that second order IVP that we solved using ODE 4.5 a couple classes ago, namely y prime plus y equals 0 with simple initial positions at 1 and initial velocity 0. To begin, we note that the characteristic equation for this DE is m lambda squared plus 1 equals 0. Why did I write m, you might ask? I don't know, because m, of course, here is just 1. We can solve this for lambda to obtain two roots and their imaginary roots plus or minus I. So we know that our general solution to the differential equation is going to be a linear combination of two complex conjugate exponential functions, e to the it and e to the negative it. So where do we go from here? Well, at this point, we want to calibrate this solution to our initial conditions, so we need to PSI. If we're going to PSI, then we also need to calculate a formula for y primed of t, which it's pretty easy to see is I c1 e to the it minus I c2 e to the negative it. And so our conditions, first initial position, implies that 1 is y of 0, which is just c1 plus c2 because e to the 0 is 1. And our second condition then is going to be that 0 is equal to y prime to 0, first of all, which is I c1 minus I c2. To solve this system of equations for c1 and c2, it's pretty much what we've been doing, except now we have imaginary coefficients. We can multiply the first one by I if you'd like, and then add the resulting expressions together. When you do so, the c2's will cancel, and we'll get that I is equal to 2I c1, which implies that c1 is equal to 1/2, and substituting that back into either equation yields c2 also equal to 1/2. If we plug this result into our formula for the general solution, we obtain a particular solution to this initial value problem, which is 1/2 e to the it plus 1/2 e to the negative it. And factoring out that 1/2 and using our trig identities, we can see that this is just equal to cosine t. And voila, from something imaginary, something real comes. So you'll notice in this problem that, of course, the values of c1 and c2 depended on the initial conditions, but whatever the initial conditions are, we're always going to have a general solution, which is a combination of e to the it and e to the negative it, and therefore we're always going to have a general solution, which is essentially some other constant c1 times cosine t plus some other constant c2 times sine t. In other words, if I look at all of my solutions to this differential equation, regardless of the initial conditions, they should all have the same period of 2 pi, but they might have different amplitudes depending on the values of c1 and c2. We can see several different examples of this in the following plot, where I've plotted 3 separate solutions to the previous differential equation with initial conditions 1, 0, 0, 1, 1, 1, where here I'm using the notation of position, colon, well really semicolon, velocity. Initial position, semicolon, initial velocity. If you compare these solutions, sure enough we can see they all have period 2 pi. But notice that when I give the system an initial velocity and an initial position, I get a slightly higher amplitude than the ones where I only give it an initial position or initial velocity. Notice also the black curve here, which was the solution in the previous IVP we saw, is actually cosine t. And notice that the blue curve, which would have had 0 initial position but initial velocity 1, is actually sine t. Now, if you're solving problems where the roots are pure imaginary, meaning they have no a in this formula here, then all those problems follow the basic structure of the previous one, although you may get different periods or different frequencies depending on the value of b. However, if your solutions have both a real and an imaginary part, then the situation is slightly more complicated and we'll get another realm of behavior, which earlier we described as the underdamped scenario. So to kind of make sense out of this new case here, let's take a look at the general solution we would get. We would get e to the a plus ib times t plus c2e to the a minus ib times t, ignoring that random mark there. If you multiply out the exponents in this expression, notice that we can factor out an e to the at from both of these expressions. And notice also that the resulting expression inside parentheses here looks like what we had before. Namely, this one is going to give us constant amplitude oscillations because we're getting pure imaginary exponents here, combinations of sines and cosines. So really what's going to happen is going to depend on this real exponent out front. Namely, if a is less than 0, like it is in physical spring mass systems, where the a is negative of the damping coefficient divided by twice the mass, then what's going to happen is that the whole solution y of t is going to go to 0 as t goes to infinity. But because I also have these oscillations, it's going to go to 0, but it's going to do so in an oscillating manner. And that ends up being the scenario that we actually saw in our real life experiment, and which sort of summarizes an underdamped spring mass system. To look at some examples, or a specific example, let's apply this kind of reasoning to the differential equation y double prime plus 2y prime plus 5y equals 0. The characteristic equation in this example is now lambda squared plus 2 lambda plus 5 equals 0, which, using the quadratic formula, we can obtain a solution -2 plus or minus the square root of 2 squared minus 4 AC, I guess I wrote it as CA, over 2A. And with a little bit of simplification, we can see that all this boils down to -1 plus or minus 2I. So this is a situation, if we're comparing this with what we did on the previous slide, we would have A, the real part, is -1, and b, the imaginary part, would be 2 here. So the general solution in this scenario is c1e to the -1 plus 2it plus c2e to the -1 minus 2it. And factoring out an e to the -t, we can see that it simplifies to e to the -t times c1 2it plus c2e to the -2it. So once again, we can see that this term out front, this decaying real exponential here, right? This one will kill off the oscillations represented in our oscillating function in parentheses there. Okay. So to conclude this video, I just wanted to show you some examples of solutions to that last problem with, again, three different pairs of initial conditions. You can see that in all three cases we get these decaying oscillations. In fact, they occur pretty quickly because that e to the -t term that we saw out front will go to 0 very quickly as t goes to infinity. So to summarize the observations in this and in general for our study of second-order constant coefficient homogeneous equations, or SOCH for short, then we know that if our characteristic equation for this has two roots, lambda 1 and lambda 2, we end up getting a linear combination of two exponential functions for our solution. If it does not have two roots, if we're in that critically damped case, then we also saw what the solution looks like, but we're not going to talk about this or get into that in this video. The first situation we saw was that when lambda 1 and lambda 2 were both real and less than 0, then all of our solutions just decay exponentially fast towards 0, and that represents the overdamped scenario. There's so much damping in our system that even the car, the mass, whatever it is, can't even get going past its equilibrium. In this video, we broke down the cases where lambda 1 and 2 are a plus or minus IB with a less than 0, and in that case, the solutions exhibit these decaying oscillations, which is the underdamped scenario. Even though it's not physically realistic, you could theoretically come up with second-order equations where a is greater than 0, and if you did, what you would end up seeing is some kind of growing amplitude oscillations over time. But that would be like some fictional example where somehow you've managed to put a negative damping in the system and feed energy in instead of taking it out over time. Finally, we also saw that if our two roots are pure imaginary, and actually you could think of this as a special case of the example above where a is 0, right? Then our solutions actually exhibit constant amplitude oscillations, the amplitude of which depends on the initial conditions, but the period of which only depends on this B term, which defines the angular frequency in our cosine or sine solutions.